Morphological adaptations of the lizard tail, Eriophyllum staccatifolium, across varying habitats in the Younger Lagoon. The morphological adaptations of plants vary based on environmental factors including water availability, soil quality, water salinity, and other abiotic factors. Our goal is to address potential physiological differences between the two populations of lizard tail. The plants on the sand dunes take a more reduced, sprawling form with less foliage, while individuals on the terrace are larger, more erect woody shrubs with abundant foliage. We hypothesize the lower dune plants will be under higher water stress in their sandy, potentially saline soils in comparison to the upper terrace plants in their loamier soil types. To explore this hypothesis, we measured water potential, leaf mass area, and xylem diameter. We expect a lower water potential on average in the sand dune plants than in the marine terrace plants. We also anticipate leaf mass per area will be higher for the sand dune plants, as plants tend to invest more into leaf mass for drought adaptation, like a succulent. We expect to observe smaller conduit diameters in the xylem of the sand dune plants. In our methods, we sampled 5 individuals from each of our 2 populations. Using a caliper, we measured the basal stem of each individual in millimeters for all 10 samples. To determine the water potential, petioles of roughly 2.5 millimeters in diameter were collected from the same 10 individuals and placed in the pressure chamber. To calculate leaf mass per area, 10 total leaves were collected and photographed next to a ruler. The leaves were dehydrated in a dehydrator and weighed with a scale. The area of the leaf was measured in ImageJ using the ruler as a scale. We then divided the mass by the area to calculate leaf mass area in meters squared per kilograms. Stems collected were cut into cross sections, stained with fluoroglucinol, and viewed under the microscope. Diameters of 15 xylem conduits per sample were measured at 10 times magnification using ImageJ. The pressure chamber results revealed that plants in the upper terrace had consistently lower water potential, indicating their xylem columns were under more tension. We found a greater average leaf mass per area ratio in the dune plants, but it was not statistically significant at our sample size. Our data suggests that plants from both sites may photosynthesize and build leaf biomass at similar rates. The xylem conduit diameters of the lower sand dune plants were larger than that in the average values for upper terrace plants. Larger conduits suggest greater water availability and higher rates of hydraulic conductance, despite the increased risk of xylem embolism. Overall, our hypothesis was rejected, with the dune plants showing less evidence of water stress despite their appearance, growth on high drainage sandy soil, and likely vulnerability to salinity stress. Studies on soil texture have shown that finer textured loamy soils in arid climates can actually be associated with more negative water potentials during drought and display greater cavitation risk than sandy soil. This is in part due to high permeability of sand, resulting in less runoff and pooling during the rainy seasons, and allowing for high groundwater accumulation and deeper root growth. This may explain why our sand dune group appeared adapted for higher water availability. We recommend further analysis of root characteristics to understand how these populations have responded to soil quality and water availability. Thank you for watching.